All right, today we're tackling one of the most famous numbers in all of physics, the speed of light. But here's the thing, we're not just going to talk about what it is, we're going to explore a really radical new idea about where it even comes from. So let's see if we can actually build the speed of light from scratch.
I mean, why this specific number? It's not a nice round 300 million, is it? It's this incredibly precise, almost random-looking value. It feels kind of arbitrary, right? And for more than a century, the answer has basically been, well, that's just what we measure it to be. It's just a brute fact of our universe.
And that's really the crucial point. The speed of light, or c as we all know it, has always been treated as a fundamental constant. You know, it's a number we discover through experiments, and then we just plug it into our equations. It's an input to our models of reality, not an output. But what if that's not the whole story? What if c isn't just a random measurement at all? What if it's a number that you can actually calculate from first principles, something that emerges directly from the fundamental geometry and the wave structure of the cosmos itself?
So that's exactly what we're going to explore today. We'll start with this cosmic speed limit, and then we're going to dive into a new model called a harmonic universe. After that, we'll gather our geometric ingredients, follow the calculation recipe, and see how c can be derived with what's called zero fit, and that's a big deal. It means no tweaking to get the right answer. And finally, we'll step back and think about what this all means for our cosmic perspective. Okay, so let's start by just framing the problem. We all know the speed of light is the ultimate speed limit, right? It's a pillar of modern physics. But its exact value has always been a given, not a deduction.
Now, to challenge that, you need a totally new framework, and the one we're exploring today is called the Harmonic Scale Framework, or HSF for short. And this model, well, it proposes a fundamentally different way of looking at the universe.
So, the core idea of the HSF is this. Just imagine that everything in the physical world, everything, all particles, all fields, are just subwaves. They're like little ripples on the surface of one single grand total wave. So instead of a universe made of separate bits and pieces, just picture one single vibrating instrument. Okay, so within this single wave, the model proposes there are 5 distinct harmonic channels. And you can totally think of these like different octaves on a piano. There are these discrete energy pathways, and they scale in a binary way, which just means each channel is double the frequency of the one before it. But, and this is key, they all carry the same fundamental mode of energy.
So the big question is, where does matter come from? Well, in the HSF, particles aren't these fundamental little dots. Nope. Instead, they're standing wave resonances. They're stable patterns formed by waves vibrating between these different harmonic channels. And fields, like an electromagnetic field, those are just propagating subwaves moving through the whole system.
Okay, so if the universe is a wave, what is it, waving on? That brings us to our geometric ingredients. To actually calculate the speed of light, this model starts with just a few very basic assumptions about the geometry of the universe.
The model proposes that the shared boundary for this universal wave is a slightly oblate spheroid. Just think of a sphere that's been squashed down a tiny bit. And it gets specific. A flattening of about 2% and a radius of just under 0.3 millimeters. This is the precise shape of our cosmic drum, so to speak. And, just like a drum can only produce certain specific notes based on its shape and how tight the skin is, this cosmic spheroid can only support specific standing wave patterns. In math, we call these eigenvalues, but you can just think of them as the allowed notes or the allowed harmonics that can exist on this surface. And they are determined only by the geometry.
All right, now for the final ingredient, and this is a big one. To make a drum produce a sound, you have to hit it, right? Well, in this model, the universe has its own internal rhythm. A base frequency for one of the highest harmonic channels, they call it the K5 frequency. This is like the universe's internal metronome. And the crucial point here is that this is proposed as a fundamental timing of the wave field itself.
So we have our ingredients, a squashed sphere, its allowed notes, and an internal metronome. The question is, how do we combine them to get the speed of light? Well, let's look at the recipe.
The process breaks down into 4 main steps. First, you set the scale. Use that pacemaker frequency and the universe's most fundamental wavelength to get a baseline speed. Second, you model the wave. You figure out how waves at really high frequencies would travel across this geometric surface. This is what's called a dispersion relation. It's basically a rule that connects a wave's frequency to its speed. Third, you find the propagation speed. Using that rule, you can calculate how fast an energy pulse, something like a photon, would actually travel. This is called the group velocity.
And finally, you get the limit. You look at what happens to this speed at the highest possible frequencies, and the average of that ultimate speed limit. Well, that's your final answer for the speed of light.
And now, for the moment of truth. What happens when you actually follow this recipe? This is where the model makes its most, well, audacious claim.
The result? The calculation produces the known value for the speed of light, and the how they get this number is arguably even more important than the what. And this right here really illustrates the difference perfectly. The standard approach, on the left, is you measure the value of c empirically, and then you use it as a given constant. You're basically fitting your models to the data. But the HSF approach, on the right, well, you derive c from geometry and wave properties. It emerges as a limit. And this is the kicker. It involves zero fitting or empirical tuning.
And the source material puts it perfectly. I'm just going to read this quote. No fitting, no empirical tuning, and no inserted physical constants. The goal is to demonstrate that the speed of light can emerge directly from geometry and wave structure. I mean, that's the core philosophy of this whole project.
So what are we supposed to make of all this? If an approach like this actually holds up, what does it mean to be able to calculate a fundamental constant instead of just measuring it?
So, why does this matter? Well, for a few really important reasons. It's transparent. All the steps and numbers are right there for anyone to inspect. It's reproducible. Anyone can go run the computation and verify the result. It's also stable. The result is a true limit. It's not super sensitive to tiny changes, so it's not just a lucky guess. And, maybe most importantly, there's no fitting. That means the model is testable. It makes a prediction that can be proven wrong, and that is the absolute hallmark of a strong scientific theory.
And that leaves us with a really fascinating final thought. We've always treated constants, like the speed of light, as these fundamental features of reality, just kind of handed to us without any explanation. But if c can emerge naturally from the shape and the vibration of the cosmos, what else can? What other deep secrets of our universe aren't arbitrary facts at all, but are written into its very geometry, just waiting for us to figure them out?